My name is Jing. Today I will present our work, Fast Transparent File System Microkernel Recovery with Ananke. This is a joint work with Yifan and my advisors, Andrea and Remzi. This is work when I was done while at University of Wisconsin-Madison. File system microkernels build a file system service and the user space process. So the file systems are running in user space without OS kernel involvement. This kind of file system recently gained more traction because of several benefits. Without the OS kernel involvement, such microkernels offer better performance for modern I/O devices and CPUs. As a user-level process, they are easy to develop and upgrade, and also leads to better fault isolation. Examples include our work, UFS, which was published in SOSP 21, and more general microkernels like Holman. File system microkernels also offer great opportunity for a new paradigm of crash recovery, process crash recovery, because the file system process crash differs much from the classic full system crash. When the kernel file system fails, it leads to a full system crash. The OS and all the application crash. Applications lose their progress. So the file system crash is treated the same as power fading. In full system crash recovery, only the on-disk states are used. So what happens when the file system is a process? When the microkernel file system fails, it only causes a process crash, not a full system crash. We have a completely new crash model and more opportunities to continue. So firstly, we can see that the OS and other applications naturally continue, which is great. The question is, can applications that are using the file system also continue? And why it is hard? The main challenge of process crash recovery is to recover the state gap. Because file system buffer update in memory, there's a state gap between the on-disk state and application view. In addition, the state gap can be changed erratically by subsequent operations or background behaviors, particularly in a non-sequential order. In this work, we built Ananke, a file system microkernel that supports process crash recovery. Central to Ananke is the plog, a data structure designed for process crash recovery. Plog is the in-memory log added into the file system process. It records the operation and other information. When the file system crashes, the OS coordinates the control transfer, notify a new file system process, and then the plog is used to recover the state gap. In Ananke, we designed several new mechanisms, plog and M algorithm to recover the state gap, kernel-coordinated speculative restart for fast recovery, and lightweight detection of corruption for more robustness. Ananke is implemented in UFS, a state-of-the-art file system microkernel. We performed thorough evaluation of Ananke, demonstrating that it offers failing transparency in over 30 fault injection experiments. We also show that Ananke incurs low common path overhead, less than 2% in most cases. Finally, the recovery is fast. Not over 400 milliseconds, even for challenging workloads, appear as a momentary performance drop to applications. In the rest of the talk, I will talk about the challenges for process crash recovery and our mechanisms, focusing on plog and M algorithm, then present evaluation and conclude. Ananke is designed to perform principled process crash recovery. The challenges are, first, to recover the state gap correctly and incurs low overhead in the common purse. The recovery also needs to be robust, such as to corruptions. We propose novel mechanisms, plog and M algorithm, to recover the state gap, and robust restart mechanism called kernel-coordinated speculative restart that also reduces the recovery time. Lightweight detection of corruption further improves the robustness. I will focus on plog and M in this talk. Plog is an in-memory log designed for process crash recovery. It logs the operations and other information. Recovering the state gap by plog is challenging. So the first reason is naively replaying each operation is not sufficient. Assuming we run several operations and then a sink flushes some of the state to disk. This is common due to out-of-order durability. During the replay, we need to ignore some operations, and sometimes only part of the operations update is needed. There's a trade-off between recovery time and common path overhead. If we cannot recover the state gap, the results will be incorrect. Likely manual efforts are needed, causing long recovery time. The second challenge of plog is to control the common path overhead. Intuitively, extra flushes can simplify the state gap, but incurs large overhead. For example, flushing every operation easily ensures correctness and low recovery time, but leads to large common path overhead. By contrast, our work at Ananke provides both fast, transparent recovery and low common path overhead. Specifically, plog and M allow us to recover the state gap without incurring extra flushes. The state gap is complicated for two reasons. Firstly, given an operation sequence, the subsequent operation may remove some operations update from the state gap, including close and sync. Close removes file descriptors. In this example, a close removes the file descriptor 3, and thus the first 3 operations do not need to be replayed. A sync of background sync makes effects durable, also removes some operations update. Besides, subsequent operation may change the precondition of previous ones. For example, in this workload, open a file, write and rename it, and sync the directory. So the on-disk states have a file named d/a. If a crash occurs after this sequence, we need to redo the write to the file, but we cannot redo the first open because the path name is no longer valid. So how to address these two issues? We design a new data structure plog that addresses the issues. Plog is an in-memory proclog that records the operations and other information. As shown in the example, a plog entry contains an array to record the possible target. The first element is the file descriptor, and the rest are possible inode numbers, including the target inode, the parent, the destination, and destination parent. It also includes a bitmap that tracks whether these operations update of those targets are still contributing to the state gap. For example, in this workload, open, write, sync, and close uses file descriptor 3, and the inode number is 5. So the first element in the array is 3, and the second is 5. In the bitmap, the first bit is set because open initializes the file descriptor. Write also record file descriptor 3 and inode number 5. The first bit is set because it changes the file descriptor offset, and second bit because the file size and contents are updated upon fsync. For the second operation write, the log interest second bit is reset because the inode update is persisted to the disk. After the close, the first element of both open and write are reset. Such design of plog allows us to track how the operation contributes to the state gap efficiently. Plog works together with an algorithm M, short for act, ignore, or modify. It enables us to transform the plog into actions that can be executed by the original file system implementation. The first decision for a logged operation is ignore or not. If it does not contribute to the state gap, it needs to be ignored. Then it decides between act and modify. Act indicates an operation will be directly replayed as it is. Modify means that an action needs to be taken, but in a modified form, such as different operation type or parameters. Let's take one step back and think about the intuition. Essentially, applications change the file system states upon 3 abstractions, including file descriptor, like the existence of an FD or the offset, or change the file inode, like write the contents, change the size. And the third is a mapping from path to inode, basically forming the directory tree and used for naming. Applications can only use the APIs to make the changes, so we list the common ones over there. We can categorize file system APIs based on the abstractions they change. Some operations only change one type, such as open for FD, pwrite for a file. Some operations change multiple types or multiple targets. For example, create initialize one FD and one file inode and changes the path inode list mapping. So the plog entry records the possible targets in the array such that the bits can accurately track how a logged operation contributes to the state gap. Either it is none, partial, or full. If the none of the bit is set, we can ignore the operation. So checking the bit is fast. The common path overhead is low. The ignore portion of M is running the common parse, so it has to be very efficient. The act or modify needs more consideration, such as what are the resulting operation types and parameters. This diagram nicely describes all the possible changes of each operation type. So the impact of subsequent operations can be seen as removing some of an operation effect from all the possible changes. So really, it's like moving towards a less overlapped region. For example, for a write operation, if the file inode is synced to the disk, the file descriptor offset change is realized by lseek. For create, if a directory and the files are both synced, open is used instead, only to initialize a file descriptor. The decision of act or modify is made during the recovery, leveraging the M algorithm and the information in the plog entries. Look at this example again. With plog and M, the path name used in the first operation will be d/a instead. This is done by keeping an on-disk view of path inode list during recovery. M scans the log entries and finds the sync of the rename. It will backtrack to find operations that depend on the path to inode mapping and update them. And we use modify for open, act for write and close, and we ignore rename and sync. Next, I present the evaluation and finally conclude. We perform thorough evaluation of Ananke, demonstrating that it provides failing transparency and fast recovery with low overhead. To evaluate the correctness of Ananke, we run the workload of file real applications and inject a full-stop process crash after each operation in a sequence. We performed over 30K experiments corresponding to different state gaps to recover. In all the cases, Ananke provides failing transparency. We compare the Ananke with full system crash recovery, the system that flushes every operation to the disk. The experiment runs level DB workload. X-axis is the timeline, Y-axis is the throughput. Ananke delivers the same level of common parse throughput compared with the vanilla system and shows large benefit over the approach that incurs extra flushes. Ananke recovery is fast. Relying on pure full system crash recovery takes a long time, potentially manual effort. Flushing every operation to the disk in the middle has reasonable recovery time, and Ananke's mechanism improves the performance of restart by using the in-memory log. The recovery time is also reduced because we pre-restart a secondary process and thus hiding the latency to initialize a large address space and device drivers. We presented Ananke, a Filesystem Microkernel service that provides fast and transparent process crash recovery. It is implemented in UFS, and we introduced novel mechanisms, especially plog and M, to recover the state gap. We conducted thorough evaluation of fault injection and overhead analysis. We show that the first system crash recovery plus the process crash recovery with plog leads to failing transparency. We propose to separate process crash recovery from full system crash recovery because file system process crash is not the same as power failing. Rather, it is a great opportunity for transparent recovery without losing the state gap. More broadly, we hope process crash recovery can improve the guarantee of local file system service in today's large-scale system to reduce the burden of global recovery. Thank you for listening. I'm happy to answer questions.